So for this video, we're gonna talk about breadth first search or BFS, uniform cost search, depth first search, iterative deepening search, greedy best first search, and A-star search, using the example of Romanian holidays to demonstrate. So first we start from BFS. BFS is a traversing algorithm where you should start traversing from a selected node and traverse the graph layer-wise, thus exploring the neighbor node. Okay, so now we're gonna look at the example of BFS using Python. On the first row, it is a function to store the data into the BFS graph. On the next row is another function called addEdge, is to add the edges into the graph, and the second row is to define the print or the outcome of the BFS graph. Next, below the mark all the vertices as not visited is to mark the vertices as not visited. In the next row, we create a queue for BFS and mark the nodes as visited and unqueue it. On the next line, after while queue, prints the outcome after it has reached the destination. Since our destination is Bucharest 13, the loop will stop at vertex 13. Next, on the function of city name is to define the vertices and the city names. Next, on the main function, defining G. Here it says that G equals to graph in which it has 100, which means that the limited vertices is only up to 100. Next, we can direct the vertices according to the Romanian map example. This is an undirected graph, so there will be 2 vertices each. An example, 1, 2, and 2, 1. So it will continue until all the vertices are visited. Next, on G BFS 1, here it says that the BFS starts at point 1. It is because our starting point is at a red 1. And so, the expected outcome, BFS uses FIFO, first in, first out queue, so therefore it visited the vertices according to their number. Next, we will talk about uniform search. Uniform cost search is the best algorithm for a search problem which does not involve the use of heuristics. It can solve any general graph for optimal cost. Uniform cost search, as it sounds, searches in branches which are more or less the same in cost. So now let's move on to the example of uniform search, which in this case uses C++. So first, the function. This part of the code creates the map, graph, and vector that we could input its value later. Next is the algorithm, which is on the line below map, is part of the code to ensure the program can connect to the nodes continuously until it reaches its final destination. It uses looping for to move to another city by index. It also uses queue to correctly make the path from initial start to final destination in order. And so finally, we can compile and run the code, and here's the result. So next we have the greedy BFS. Using a greedy algorithm, expand the first successor of the parent. After a successor is generated, if the successor's heuristic is better than its parent, the successor is set at the front of the queue with the parent reinserted directly behind it, and the loop restarts. Else, the successor is inserted into the queue in a location determined by its heuristic value. The procedure will evaluate the remaining successors, if any, of the parent. So now, we're gonna go through an example of GBS using C++. At first glance, GBS can look very much the same with A* search method. The difference lies at costs used to make the decision. Here we create the maximum edge and nodes. Next, here the node and comparing function using struct node. Here, we use the method decision taken by the program takes into account only the heuristic value and pick the option with the smallest value. Heuristic values are estimated costs that it takes from the node to its destination. Next, we create the main program, making it easy for changes. We create the program that takes input, in which we can see the code below. Here we've input the heuristic values for each location. Each location is represented by a number. Next, the data of Romania can be seen here. First, the source is Arad, which is set to number 4. The destination is Bucharest, and it is set to number 3. Here we input the number of nodes and edges, and here is the input for every edges the graph have. And now we input the source, which is Arad, and the destination, which is Bucharest. The output would give us the expansion route the search takes. So next we have iterative deepening search. This algorithm works like depth-limited search of depth-first search algorithm, but it runs repeatedly with increasing depth limits until the goal is found. And here is an example of the program
itself. Okay. In here, I will use Python as my programming language. So the first one is the initiator. So I initiate the problem, become a graph. Okay, so this is the graph. Okay. As we can see, we can relate this with the picture. Sorry, with the picture. Okay. Ah, pardon. Okay. So I will initiate the first one. This one. It will be the root or the parent. Then on the right side in the array, it will be the child node. So for example, Arad have a child is Timiswara. You can see in here. Then Zerin in here. Then and CView you will find in here. So after Zerin have a child Oradia, Timisoara have a child Lugoj, as we mentioned in the code. Sibiu have child Fagras and Remucoversia and Fagras. So exactly like that. So we continue to our algorithm. So the code it have two section that two function. The first one is the iterative deepening depth first search algorithm and depth limited search algorithm. So the code itself it uses two algorithm actually. The first is depth limited search algorithm for comparing the goals to something that we search, the current node that we map, that we found compared with the goal. Then the second algorithm is IDDFS, or I call it iterative deepening search. It will compare whether the result and the goal is the same or not. If not, then the depth limit will be increased by 1. Exactly like that. And the last one, this is we'll set the initial state, then the goal state. Like that. Okay, let me explain the first function is the IDDFS algorithm. So we set the depth will be 0 because in the depth 0, then in here we will do a looping algorithm that loop the result. Actually not just a result, it's all of it. So this will be loop the DLS function, then it will print the result and the goal if the result is found. Then this is the increment of the depth. If the result not found, so we increment the depth. And the second function is DLS, the second algorithm. In here we see the if and elif statement. So the first one is if the depth is 0, then the end node is equal to goal. So we have found the goal. This is mentioned that when the node that we visit is same as the goal, so we found the goal. Then we return the node. So else, if the depth is more than 0, so we'll be loop the children. Then we will compare it, the goal with the child itself until it found. Then return the goal. The goal that we return, it will be returned to IDDFS goal for the comparing. Then found, we will print result and goal, and that. Let me run the code. Okay, so the output of the code, the output of the program will be like this. Like you can see, it's just like looping at depth 0. So at the depth 0, the node is Arad, the goal is the Bucharest, depth 0. So result is known because Arad is not the Bucharest. So we loop at the depth 1, the node is Arad, goal is Bucharest, the depth is 1. Because the depth is 1, we found in the depth 1. So we're looping through the children of the Arad. Arad have children Timisoara, Zerin, Sibiu. So we will first search in the Timisoara node with the depth of 0, then Zerin, then Sibiu. So as you know that Timisoara and Sibiu is not the Bucharest, so the result is known. Because the result is known, the depth limit will increase to 2. So increment to 2. So because this is iterative deepening search, so it will start from Arad again. So not the Arad, first Bucharest, but you can see the difference between this result, this output, comparing to the above output. Is the depth is 2, not a 1, because we increase the depth limit. So we start from the children of the Arat, Timisoara, Serin Sibiu. Then we know that the children of Timisoara is Lugoch. Okay, we will show the code. We will show the picture. Okay, the child of Timisoara is Lugoch. So we will looping through the children Lugoch, and we will try to compare the Lugoch with the goal. Then we move to the Zerin. This is Zerin. The goal is Bucharest in the depth 1. So because this is the depth 1, so we will visit Oradea and compare the Bucharest. It's not the correct goal, so we try to search in CBU with the depth 1. So because this is the depth 1, so the depth 1 of CBU is CBU child. CBU's child is Fagaras and Remicophyllisia. Fagaras and Remicophyllisias. Fagaras and Remicophyllisias. At first we will find in the Fagaras. So we'll find the Fagaras. As we know that Fagaras is not Bucharest, so no. Remico also not a Bucharest, so yeah, the result will known. The goal is still Bucharest. So because we can see, so we're looking at the depth 3. Depth 3. Depth 3, it will the child of Fagaras, Remicophyllisia, Oradea, Lugoch, and so on. Okay, and we start from Arat again. Arat with the depth of 3, looping through Timisoara. As I said before, as I mentioned before, that it's exactly like a depth first. So we will find in the we will try to search in Timisoara at first. So this is Timisoara with depth 2, so it will be looped to the Lugoch. This is Lugoch with depth 1, so it will be moved to Mehadia. Then check the Mehadia whether this is the goal or not. So it's not the goal, so okay, we will move to Zerin from Arat with the depth 2, because this is the depth 2, so it will be iterated under Fagaras and Remicophyllisia. Okay, depth 2, looping through children Oradea. The not Oradea will be looped through children CBU because the depth is 1, CBU. So in CBU, we not this is CBU is not the goal, so okay. The next is we will search through CBU. CBU have a depth 2, looping through children Fagaras and Remicophyllisia. The not Fagaras have a depth 1, so we will search the child of Fagaras. Then we found a Bucharest in here. So depth 1, looping through children Bucharest, not Bucharest, goal Bucharest, depth 0, found goal, returning result Bucharest and goal Bucharest. So as we know that the result will be Arat, CBU, Fagaras, and Bucharest. Okay, thank you for listening. I hope you can understand what is iterative deepening search. Okay, bye.
Next, we have the A-star search algorithm. Unlike other traversal techniques, it has brains, which means that it is a really smart algorithm which separates it from other conventional algorithms. It is also worth mentioning that many games and web-based maps use this algorithm to find their shortest path very efficiently in approximation. So now let's move on to the example of A-star search. First of all, we create the node and its comparison. And next, we calculate the heuristic works decision taken by pick the option with the smallest value. And then we created the input based on the number of nodes, the number of edges, then created input the path and its cost one by one. In the end of the code, we state the heuristic cost to be calculated based on input. And so here is the heuristic cost. And next we have DFS or depth first search. Depth first traversal or search for a graph is similar to depth first traversal of a tree. The only catch here is, unlike trees, graphs may contain cycles, so we may come to the same node again. To avoid processing a node more than once, we use a Boolean visited array. And here is the example to DFS using C++. Okay, so that is all for now. Thanks for watching.